The graph of sine y minus sine x equals cos squared of x minus cos squared of y is empty, non-empty but includes no straight lines, includes precisely one straight line, includes precisely two straight lines, includes infinitely many straight lines. So when you take one look at this equation, you can see it involves, well, namely x and y. It is an implicit function in that we don't have x or y made the subject. And moreover, well, on the left, we have sine of those x and y Cartesian coordinate axes. And on the right, we have the cosine squared terms of the x and the y itself. So when you first look at equations like this, I mean, within the first 10 seconds, unless you're something of a genius, you're not going to be able to see or gauge some insight as to how this looks. So you just need to start somewhere. Take a hunch, take your intuition, play around with it, see what you can do, see what insight you can draw out, try and tease out some symmetries and use everything you know about the sine and cosine functions themselves to try and make some sense of this particular equation. And again, I always say this is don't forget that when we say the graph, we literally are just plotting the infinite set of solutions to this particular equation. X and y are two variables, and this is one equation. And that typically leads to an infinite set of solutions, typically, not always, but typically. And those infinite set of solutions are what we're considering when we consider the graph. So when I first looked at this question, my initial intuition was to swap the cosine squareds out for sine squareds, because I'm just used to doing that, because it gives you, it would give you a quadratic in sine, albeit in x and y, but it's going to get you started. So let's go ahead and do that. And I'm going to do that using the good old trig identity. Sine squared plus cos squared is 1. Doesn't matter what the input is. And that allows you to swap the right-hand side out here. Well, the cos squared is what is that? It's the 1 minus the sine squared using the identity. And that was the x there. So you get, that is the cos squared. And then you're minusing the cos squared of y, which would be 1 minus the sine squared of y on the right-hand side there. And you can see how the ones would cancel here. When you minus those brackets and then you minus, that gives you plus. So you get the sine squared of the y and then minus the sine squared of the x. And that would equal the left-hand side, which is now sine of y minus sine of x. Okay, all right. So this is definitely a step in the right direction. And at this step, you might be tempted again to get it all to 0, maybe try and solve it in that way, because ultimately, we do have a quadratic in sine of y as well as sine of x, just kind of being added up and then set to 0. But that wouldn't be the best approach here. Solving two quadratics, especially quadratics which involve x and y in the same equation, I can't see an easy way of doing that. But if you take another look at this equation here, you can see how if you add the sine squared over to here, and if you minus the sine y over here, we are going to get the same thing on both sides, just with the x and the y kind of interchange. So if you add the sine squared over here, you get sine squared of the x minus the sine of x. And if you add this sine y minus the sine y over here, you get sine squared of my y minus sine y. And you can further factorize that if you like. I'm going to go ahead and do that. I just think it makes things a bit nicer to look at. So there we go. And here we go over here as well. Now, this is a crucial insight. If you look at both the left-hand side and the right-hand side, you can see x and y are playing the same functional role. What do I mean by that? Well, I mean, if you were to call the left-hand side a function of x, where x itself is the input, then the right-hand side, likewise, would be that same function f, just with the input as y. And moreover, for this particular graph, the outputs of those functions are going to be the same. So this function f of x is, you could define it to be that as the output. And this graph is going to have lines such that f of x is equal to f of y. So this is saying the output from f when you put x in is the same as the output from f when you put y in. And a trivial solution to that equation is going to be when the y equals the x itself. because that's just saying the inputs are the same. If the input is the same as f, the output is going to be same from the f, because the f itself is not a multi-valued function, okay? For a given input, there's a given unique output. And therefore, if the inputs are the same, the outputs are going to be the same. And therefore, solutions of the form y equals x are going to be a trivial solution to this particular equation. And therefore, that's going to give us one straight line on this graph. But that wouldn't be the only straight line. There's a lot more to be said here. If you take a further look at this function f, you can see how the input x, ultimately it goes into the sine function itself in both instances. And a way of expressing that is, you could express the left-hand side as a composite function of x. So you could write it as some other function g and then of sine of x, like that. So this is a function of the x input. And here the g of a would just be defined to be the a times the a minus 1, okay? And because as a composite function, the input ultimately goes into sine, we can take advantage of all the symmetries of the sine function itself. And there are many symmetries to the sine function. One of the most obvious symmetries is periodicity on the sine function. So let's take a look at that. If you draw the sine function on a graph, it looks a little bit like this, right? So here the inputs are on the along axes and the outputs are on the up axes. And if you plug an x value in here, you get an output sine of x, but that's not the only input which gives you the output of sine of x. There are other inputs here. This one right here, that one there is actually pi minus x. And also this one over here, that one's just 2 pi ahead of that one. So that's illustrating the periodicity of sine in that if you add 2 pi to the input, it doesn't change the output, okay? And you can do that as many times as you want. So if you add 2 pi, add 2 pi, add 2 pi, or maybe minus 2 pi, so on and so forth. This is what we generally refer to as periodicity, the period of the repeating unit. And the periodicity of the sine graph is 2 pi itself. And this is going to be crucial for this question, because what it's saying is if you add 2 pi to the input for sine, it doesn't change the output. And if you look here, we have a composite function g of sine of x. So if you add 2 pi to the x here, the output from this composite is going to be exactly the same. So that's going to give us many lines, right? Because the input could be x here to give us the same output y, but the input could also be x plus 2 pi, or plus however many 2 pi's you want, or maybe minus 2 pi's. And this right here is going to give us an infinite set of straight lines in that you can always just do x plus however many 2 pi's you want. So 2n pi, where n is an integer there. That right there is an infinite set of straight lines, which is going to exist on the graph, which plots these solutions to this particular equation. So once you realize that, you could just circle the letter E and move on. But I'm going to go ahead and tease out a few more things here. So there's another solution to consider here from this pi minus x. If x is the input to sine, the output is sine of x. But if you take the input to be pi minus x, you get the same output as well. And that's going to be the same down here. So again, another solution to the y could be pi minus x, like that, or you could plus and minus 2n pi to that as well, and you get this. You get 2n plus 1, lots of the pi, and then minus the x, okay? So that right there, that gives us another set of infinite straight lines. One set of straight lines has a gradient of 1, and the other set of straight lines has a gradient of -1. So here's my gradient of 1 there, and here's my gradient of -1. So let's go ahead and do a quick plot of those lines that we are talking about. What are they going to look like? Well, we had the trivial y equals x. That's nice and easy, right? That's just passing through the origin with a gradient of 1. So here's x and here's the y. And y equals x is going to be, let's do it in the green here. So this is y equals x right there. Okay, y equals x. We also have y equals x plus 2 pi, because you can plus and minus as many 2 pi's as you want. And that would be looking a bit like this, or maybe minus 2 pi would be looking a bit like that, okay? So that's y equals x plus 2 pi, and so on and so forth. Okay, there's my infinite set of lines. This right here, intercept of 2 pi, and this right here being the -2 pi. Okay, but that's not the only straight lines. We had the y equals pi minus x, and then just plus or minus as many 2 pi's as you want. And that's going to be a gradient of -1. So here's my pi, and then minus the x. Looks a bit like this, okay? These are going to be solutions to this equation, again, because of that degeneracy in the inputs to sine. So this is the y equals the -pi minus x curve, and likewise, you can go plus or minus 2 pi as well. So if you went down to -3 pi, that would be looking a bit like that. And you can clearly see we're going to have an infinite set of straight lines on the graph of this equation. But that would by no means be the full picture. There is actually lines on the graph of this equation which aren't straight lines. Maybe not immediately obvious from the way I rearranged it to begin with, but let's take another stab at this. So we had sine y minus the sine of x, and I swapped out the right-hand sides in terms of the sine squared, so that gave me the sine squared of the y, and then minus the sine squared of the x, okay? Now this right-hand side is begging to be factorized. It is the difference of two squares in that you have one thing squared minus another thing squared. So again, you can always factorize that. A squared minus b squared is always the same as a plus b times a minus b, right? That's the difference of two squares. Crops up all the time. And we can do that here. So sine y minus sine of x is the same as sine of y plus sine of x times with sine of y minus sine of x, like that. And you'll notice we have this factor here is just the left-hand side. So sine of y minus sine of x is that factor there. So one thing you could do at this point is bring all the terms to one side, but keep this factor factorized. So what am I going to do? I'm going to get a 0 over here, but to achieve that, I would be minusing 1 lots of that factor over here, and that -1, it can come inside this this factor here. So sine y and the sine x, and then just minus the 1, and then keep that factorized with the sine y and then minus the sine of x. And perhaps this this way of writing the equation is even more suggestive than the way I originally took a stab at it, because we have the product of two factors equals 0. When any one of those factors is 0, then that's going to be a solution. In particular, the second factor here we've already considered, because that was the sine y equals the sine of x. And I argued that point from a more kind of functional perspective here, in that x and y are playing the same functional dependence on the sides there. But you can see it creeping up again here, and setting sine y equals sine of x would give you exactly the same solutions as these ones up here. But this factor here, we haven't considered the sine y plus the sine of x minus the 1. That would equal 0 as well as solutions to this this particular equation. And well, let's go ahead and write it down. So sine of the x in addition with the sine of the y equals 1, right? Now, I'm not going to try and solve that for any particular y in terms of x or x in terms of y. That's just going to be ugly. I don't think there's too much more you can do with this equation, but it does definitely have solutions, right? One solution would be, for example, if you plugged in the value of x which sends sine to half. What is that? That's the pi over the 3, isn't it? So if you plug in the x as pi on 3, and you plug in the y as the pi on 3, then you would just get the half and the half being added up to the 1. So that'd be one particular solution. And you can see how, if you think about how sine behaves in between negative pi on 2 and pi on 2, it's a positively increasing function. So the gradient is always positive between those two bounds. So you can see how if I was to increase the x value here, then the y value would necessarily have to decrease. And that's going to give us an infinite set of solutions to this particular equation. So to gain some more insight into this function on the left-hand side, I have gone ahead and plotted it in a 3D graph plotter. And here's what I'm dealing with. So this right here is a 3D graph plotter. This axis here is the x-axis, this axis here is the y-axis, and this axis here is the z-axis. And what I'm going to do, I'm going to plug in sine of x, just to give us a feel. So you can see how the x-axis is protruding off towards the left there, and this is drawing the graph of z equals sine of x. So this is the z-axis up here, and z is equal to sine of x. So if I rotate this around a bit and then come on down, you'll see we just have the ordinary sine of x graph. There-ish, right? There, right. That's what sine of x looks like when you draw it on a 3D graph of z equals sine of x. But obviously, if you were to put in sine of y, that's just going to kind of rotate it. So this is the y-axis, and you can see how, a z equals sine of y gives you the sine graph looking a bit like that. Now, imagine what happens when you add these two things up. Well, where the sine was 1, which is at pi on 2 right there on the y, and sine of x was 1 when x is pi on 2. When you add these up, you're actually going to get a value of 2. So watch closely as I add sine of x to this. So let me add sine of x. Add sine of x. There we go. That's what we get. So you can see how we're getting that peak right there-ish. You see that? Yeah. So that peak there would be 2, because 1 plus 1 is 2. And it would be happening when the x and y values are actually equal to pi on 2 and pi on 2 themselves. Now, I'm not trying to solve sine of x plus sine y to 2. If we go back to that equation I had again, we had sine of x plus sine of y equals 1. So imagine looking at this this 2D graph plot. Imagine the plane passing through the z equals 1. It's going to be a horizontal plane parallel to the xy plane here, just shifted up by 1, and it's going to be cutting. It's going to be cutting this surface at an infinite set of points. So let me just rotate around. There we go. Okay. Now you have to imagine the surface of z equal 1. That's going to be around about here-ish, I'd say. And imagine it cutting that green surface. And when it cuts that green surface, that's going to be the infinite set of solutions to this particular equation right here. Now, I have actually gone ahead and plotted those on another graph. We don't need a 3D graph. We can just use a 2D graph. And here's what they look like. So this is the sine of x plus sine of y equals the 1. And we get this funny shape here. So you can see this is when x equals pi and y equals 0. That's going to be a solution right there. This is when the x equals 0 and y equals pi. That's going to be a solution. And I also mentioned the pi on 4 solution right there. Sorry, not pi on 4, pi on 3. Yes, pi on 3 which would be right there. So that's all the solutions to sine of x plus sine of y equals 1. I'm not sure, and this would be what that, if you imagine the z equal 1 plane cutting that green surface, it would cut it and form contours like this. It would form contours like this. And you can see we get an infinite set of solutions and it gives us this funny shape. But moreover, because x and y are within sine, again, we're going to have periodicity to consider. So if you add 2 pi to x or maybe to y, you're going to get the same solutions. So if you zoom out a bit here, we actually get an infinite set of solutions, all just kind of 2 pi away from each other. So this is the contour plot, which, this is the graph, you might say, which of the infinite set of points which satisfy that particular equation. But that obviously wasn't the only solutions to our problem. Our problem was originally this equation here, sine y minus sine of x equals cos squared of x minus cos squared of y. And we had these considerations where sine y equals sine of x as well, and that gave us these straight line solutions, right? These are the ones which we dragged out using a bit of logic and reasoning. So if we go back to Desmos here, if I plot that graph as opposed to that one, you can see we get those infinite set of straight lines along with those funny curved solutions. I'm not sure if that shape has a name. If it does, I'm not aware of it. But that's the shape where sine of x plus sine y equals to 1. And these straight lines are where the sine of x is equal to the sine of y. And they're going to intersect right here when the x and y is pi on 3. And they'd also intersect up here where the x there is the pi minus pi on 3, again, taking advantage of the symmetry on the sign. So this would be 2 pi on 3, that point right there. So I think that more than answers this question. The answer is going to be part E. We have infinitely many straight lines.